Okay, sorry for that. As I said earlier, the main focus of this work, of this presentation, will be the methodology of the numerical model development, the results of the numerical analysis, and the major outcomes regarding these three major case studies. I would like to give you an overview and an introduction on how numerical analysis can contribute for the reduction of greenhouse gas emissions and how it is related to climate change. Environmental pollution is a daunting challenge for our civilization, and the sustainable development is the key aspect recognized globally by all governments. The greenhouse gas reduction is the primary goal in the effort against the impacts of climate change. And we know that regulations and policies and frameworks were and are being developed by the governments and are implemented as well. The 2030 European Union package sets targets of 55% reduction of emissions compared to 1990 levels. This brings us to the construction sector, which together the sectors of buildings and construction sector account for 27% of all energy sector emissions and 30% of all the final energy consumption worldwide. Building envelopes and material configuration can directly affect the heat transfer through the building envelope and have a huge impact on energy saving. And the technological advancements in building materials and building design are rapidly expanding, and effective solutions are promoted to the market for more innovative and sustainable buildings. Concerning the numerical tools, the concept of numerical investigation involves the calculation of the thermal performance of building envelope with predetermined material properties and boundary conditions. The need for the development of building efficient techniques push the situation where software tools can be utilized to investigate complex geometries and flow fields. And numerical tools are utilized to predict and improve the thermal performance or capabilities of a building configuration. Numerical investigation. This work numerically investigated three case studies, major case studies. The first one concerns a double skin facade building element, which was integrated into the building envelope. Also, the second major case study was building elements that were enhanced with phase-changing materials. And the first case study was a solar thermal system, which was integrated into the building envelope. Regarding the double skin facade, this system is composed of two layers that allows airflow through the intermediate cavity. The ventilation inside the cavity can be natural or mechanical and can absorb or release heat. Also, the system can be optimized based on the building energy requirements and ambient conditions, and is an established solution with potential to improve the thermal insulation, performance and comfort, and also reduces heating and cooling demands of the building. A phase-change material is a substance that during a phase transition releases or absorbs enough energy to deliver usable heat or cooling. The transition usually takes place between solid and liquid phases, which are the two basic forms of matter. PCMs can be used in buildings to improve their efficiency by reducing heating and cooling needs. And recently, the use of PCM in construction has drawn more attention, particularly when it comes to concrete, which is the most common material used worldwide. Here we can see the cycle of the PCM. When the temperature rises, the PCM absorbs heat, it becomes liquid, and in the night, when the temperature falls, it rejects the heat and goes back to a solid form. Regarding the solar thermal collector, a solar thermal collector is a device that collects or concentrates solar radiation from the sun. The solar collectors are primarily used for active solar heating or allow for heating of water for personal use. The use of these solar collectors provides an alternative for traditional domestic water heating using a water heater, potentially reducing energy costs. Here we can see a cross section of a solar thermal. We have the fluid input, the fluid output, the different materials, and the solar radiation that is being absorbed. Firstly, I would like to point out the innovative aspects of these case studies. Regarding the double skin facade numerical model, the double skin facade was integrated into the building envelope, and this allows for constant supply of air temperature through the building shell and constant airflow through the building shell. For the phase change materials, we investigated phase change materials for various orientations, north, south, west, and east, and also the phase change materials were investigated under transient state conditions. And the third case study was for the building integrated solar thermal, which was investigated for various inclination slopes, also for transient state conditions. And the third aspect, which the water consumption of the system was accounted. Secondly, I would like to introduce you to the methodology. The approach of this numerical model development was the geometry design, was the material properties configuration, was the physics configuration, then boundary conditions configuration, and the study configuration, the solver of the software tool. For the geometry configurations, we investigated 6 geometries regarding the double skin facade numerical model. For the PCM, we had building configurations with brick and stones, and they were 25 in total. And for the building integrated solar thermals, we had 3 total geometries. What we changed in the numerical model, what we changed in the geometry for the double skin facade was the material addition and placement and the cavity height and width of the double skin facade. For the PCM, we added and removed insulation, we changed the thickness. We also added materials and the placement of the materials, as well as we investigated the same geometries without the PCM. For the third case study, the riser of the geometry of the riser was changed, and also the riser fluid flow pattern was changed as well. Here you can see the materials used in each case study. For the first case study, we have gypsum board, cross-deck, glass mineral wool, thermal board, and clay brick. For the PCM study, we have perforated fired clay bricks, stone. We have joining mortar, cementitious repair mortar plaster, XPS, extruded polystyrene panel, and the phase changing materials. And for the third case, we have the glass, the aluminum, copper, polyurethane, mineral wool, mortar plaster, and clay bricks. For the software, we used SolidWorks and COMSOL Multiphysics, which are computational fluid dynamics softwares and finite element and analysis. The first equation that was utilized in the software was the conservation of energy, the conservation of mass, the heat conduction equation, and for the PCM case, in addition to the first mentioned equations, the apparent heat capacity, where this equation accounts the specific heat for phase 1 and for phase 2 during the phase change transition. For the boundary conditions, for all the cases, we had the ambient temperature, which was in the form of a dynamic profile, solar radiation, which also was in the form of a dynamic profile, and these were changed for each orientation. These data were extracted from the well-known PVGIS tool, and each model was differently configured. For the first case, for the double skin facade case, we used the TSOL formula and calculated the values of the TSOL, and these were imposed as external temperature profiles. Regarding the internal conditions of the first model, the internal surface was assumed to be 22 degrees Celsius. For the PCM case, we repeated the same methodology. We calculated the values of the TSOL formula, and these were imposed as a dynamic profile at the external wall of the surface. And for the internal surface, 20 degrees Celsius was assumed. For the built-in integrated solar thermal model, these were dynamic conditions. On the left, you can see the first case. Excuse me. This is the second. Sorry. This is the second case. You can see the internal temperature on the right, on the left. On the right, where the external temperature was imposed. Here we have a thermal isolation, and we have the PCM layer. This is just one case study as an example. On the right, we can see the built-in integrated solar thermal model. The red arrows indicated the ambient temperature, which was dynamic, and the yellow arrows indicated the solar radiation, which was also dynamic during the simulation. For our double skin facade case, the yellow lines indicate where the air pathway was located. So this is the double skin facade integrated into the built-in envelope. On the bottom, we see the blue line. This is where the internal temperature was imposed. And on the top layer, this is where the external temperature was imposed. And on the left and right, we assume that no heat loss occurs. And is a thermal insulation. Now I'd like to proceed to the results of this numerical analysis. So for the case studies of double skin facade, we extracted the following data and processed them accordingly. We have.
Look, I'm sorry for interrupting, but on my screen I cannot see the data. I don't know what the rest of the people are looking.
Cumulative heat flux, total energy.
All right. Okay, I can see. All right.
I have examples, graphical examples later.
Okay. All right. Thank you very much. Continue, Beto. Thank you.
Okay. So the first thing that we extracted was the cumulative heat flux, and this was done for non-static versus static system. So we numerically simulated the system without the airflow through the double skin facade, and how it behaves when we supply it with constant airflow and constant air temperature. And this was done for January, April, July, and October, and for orientations. Next, we have the total energy savings in kilowatt hours per meter square per year. And this again was done for non-static versus static system for January, April, July, October, and all orientations. And the total energy saving in percentage for the same conditions. This is a graphical representation of how the results were graphically presented, and these were done with Python heat maps features. So on the left we have the January non-static, we have the January static. On the bottom we have the different orientations, and each value represents that particular case. With the same principle, we can see the total energy savings for different parameters. This is an extracted animation from the real numerical models. Here we can see how the temperature changes, and on the left you can see the time. So this particular study was done for 72 hours, and as you can see, this is how the numerical model behaved for this particular case.
The top one is the external?
The top one is the external temperature, and you can see that the internal surface temperature was the same.
And the 72 is 72 consecutive hours.
Yes, this is
day, night, day, night, day, night.
Yes, and this is just to get a real representation of how the system will actually behave in real life. For the second case study regarding the phase changing materials, again we have the cumulative heat flux, the total energy savings, and the energy payback period for with years. Here we compare different configurations, and as earlier mentioned, we have configurations with brick, with stones, with different materials, with more or less insulation, and also the placement of the insulations was altered during the simulations. And this was done for Nicosia, Athens, Milan, and Copenhagen in the case of cumulative heat flux. In the case of total energy saving, we have Athens, Milan, and Copenhagen. And for the energy payback period, we have all orientations in Athens, Milan, and Copenhagen. Here we can see again an example of the generated heat maps using the extracted data from the numerical softwares. We can see the total energy savings per year in kilowatt per meter square for all the configurations based on each orientation. And here we can see the energy, the calculated energy payback period of years for, excuse me, this should be orientation. This is a mistake. And for each case. And again, this is a demonstration. This is an animation I recorded with the software tool. Here you can see a brick case study. This is the air force of the brick. We have the insulation, we have the PCM material, and on the right we can see how the surface temperature changes through time. And on the left we see the internal surface temperature. And this simulation was repeated for 96 hours. The third case study was for the building integrated solar thermals. And here we observed the system fluid temperature. Again, the system fluid temperature where we compared the systems. And here was the system fluid temperature where we compare the systems with and without the water consumptions, without accounting the water consumption. And the total daily heat flux through the building masonry, and when we have solar and when we don't have solar system. So one simulation was done with the building integrated solar thermal and one was done with another, and we compared the daily heat flux. For the consumption, we accounted, this was done for south orientation for November and August, and for an inclination slope of 90 degrees. For the fluid system temperature, where we compared every system, this was done for all orientations for Nicosia for November, January, March, August, and for all inclination slopes. On the left, you can see the average system temperature, and this indicates the uniformizer system, the martyrizer system 1, and the martyrizer system 2. And you can see for each slope the different temperature that the fluid system achieved. And on the right, you can see the total daily heat flux inwards and outwards of the building when we have a solar thermal integrated into the building envelope and when we don't have. This is the demonstration of the third numerical model. Here you can see the simulation repeating. I think that was done for 4 days. And as you can see, the purpose of extending the cycle is to let the system behave as it will behave in real life. And see, you can see the temperature of the fluid inside the system rising and through time. Next, I will point out the major outcomes of the 3 case studies. Regarding the double skin facade study, constant airflow and temperature were identified as critical factors, significantly reducing heat transfer through the building envelope. This was the first major outcome of the case study. The second was that the internal surface temperature of the building envelope was observed to be relatively constant under diverse boundary conditions, and this was observed when the system was in a non-static state, which means that we were constantly supplying air constant air flow and constant air temperature through the double skin facade. The streaming flow through the building envelope acted as a shield barrier, minimizing the heat absorption and adsorption between the internal surface, even at times when the surface temperature deviation between the internal and external domains was 30 degrees Celsius. For the case study of PCM, we observed that the cumulative heat flux to the building masonry was significantly reduced when the PCM was integrated into the cement-based mortar material. Also, the significance when the insulation was placed at the exterior of the masonry instead of the interior. Therefore, the placement of insulation at the external is more effective. The total energy savings per year for building envelopes incorporating phase changing materials occurred under colder conditions. This is another observation. And for warmer climate conditions, the optimal orientation incorporating PCM into the building envelope was east, and for colder climate conditions was north orientation. These were the best orientation for the maximum thermal performance. Finally, for the case study of building integrated solar thermal, the riser system, which consisted of a group of interconnected risers with a single input and output, was capable of heating the fluid more efficiently and achieving higher riser output temperatures. The second finding was that the study indicated that the heat flow windwards building masonry when the hot water wasn't fully depleted from the system. So we had hot water, even at night we had constant heat flux going through the building envelope. And the third outcome was that the water consumption profile consideration indicated a change in numerical results output. So the accuracy when numerically investigating solar thermal systems was changed, and is also identified as a clear factor when assessing the thermal performance of such systems. And this was the last page. Thank you for your time. If you have any questions, please feel free to ask.
Luca, thank you for the presentation. Catch your breath so you can we can move forward. Congratulations on your work.
Spelling some words.
You have to make bigger with talking so that we can see.
Shall I? Shall I close the presentation or?
Leave it, Luca. Let's just see how it goes, and then we decide in the process. Okay, my suggestion is just go around, and if everyone has questions or comments, to ask Luca. And you are.
I would like to start with some questions. I don't know, can you hear me?
Yes, I think you should go first, Barry is the advisor, and then I will go last. So each one can take his turn and make comments. All right, go ahead.
I'm coming close to the microphone so that it's better for the people to hear me. So first of all, I would like to congratulate Loucas for his work. Loucas was a full-time researcher with us for the past 3 years, and the fact is that he delivered a great amount and quality of work. What he demonstrated was a result of some research projects in which he was actively involved, and actually it's not his entire work. He did much more that he didn't present today, but when he was to draft his thesis, we just sat down and said, okay, let's take some case studies which constitute a whole, let's say, case, and let's present those. Now, what I would also like to mention is that out of his work, as of now, Loucas has 6 publications in well-established journals. 3 are data sets and 3 are research papers. And he's also expected to publish, or he has submitted another 2 studies which are expected to be published in the following months. So the one is with minor revision and the other one is with major revision, but I think he will make it through. So having said that, I would just like to congratulate Loucas. And seeing his presentation now, I realize how much he achieved these past 3 years that we have been working together. Loucas, congratulations. It was a great pleasure to work with you. Now, I just have a few questions for Loucas. You did a numerical simulation, and as we have discussed this many times, we cannot rely just on numerical simulations. We always need to have the experimental results. And this is something that Alexandros also understands very well. I myself, because my PhD was in the experimental fluid mechanics, so we know well that you can always have nice colors and nice configures with simulation, but you can never trust them if you don't validate them. And what I would like to ask you is to brief us a bit about the validation procedures that you followed for your results, because you didn't mention anything in your presentation for validation. Can you give us a few words for each case study, which validation procedures you followed?
So regarding the case study of double skin facade, this was a project which Crosswise Limited was involved, and they actually built the test cell that I numerically investigated. There we had our weather station, a Hobbolink weather station, which we measured all the ambient conditions. We had ambient temperature, we had the wind speed, and pretty much every ambient conditions that you can get. Regarding the internal surface and external surface of the test cell, we measured the temperatures, and this was done through the use of thermocouples. We installed thermocouples on the inner surface of the building and the thermocouples on the outer surface of the building. And these were connected to a data logger, and all data were measured for at least 2 years. For the validation model of the particular study, we retrieved those data and the measurements, and I wanted to repeat the numerical simulation and compare my internal surface temperatures compared to the measured internal surface temperatures, and in addition to that, instead of using my external temperature profile, I used the measured experimental temperature profiles. The results were positive. Actually, we calculated the numerical results error with the use of root mean square deviation formula, and this was under 10%, which typically is accepted and as a good value for when validating numerical models. So regarding the second case study,
Yes, it's okay.
Okay.
So, all right. Thank you for your answer. Look, we don't need to refer to the other 2 case studies.
These were done in the same principle. We retrieved data from the experiment and put them as boundary conditions in the numerical models.
So I have another 2 questions for you. The first one concerning, okay, I'll leave that one. I have just the last question for you. It's a personal question. So you started about 3 years ago in December 2019 with your work. And now we're in January 23. Going back when you started and seeing your progress and development, can you just shortly describe those fields that you have been able to develop during your PhD, and can you make, let's say, a flashback and see how you developed yourself these 3 years?
Yes. So the first thing that I was struggling at first was how to approach a numerical model development. And as I mentioned earlier, the methodology that I created, this helped me a lot to and saved me a lot of time to have this approach, because it's something that I did a lot of trial and errors. Okay, when I started, also a big problem was managing all those boundary conditions data, extracting them from a website, processing them in a correct way where you can interpolate them into the numerical model. This usually takes a lot of time, and for sure I developed. I developed a good skill on doing that. I think now I will be much faster than the first time. The second challenge that I faced through this journey was the error from the numerical model. So the basic principles of the numerical model analysis, usually if the solution does not exist, then the numerical model never ends, and also you get the very nice error. So that took me a lot of time and logical thinking on how to properly set the boundary conditions. And at the end of the day, this was much simpler than I thought.
What about the physics?
Also the physics. This is another thing that I was struggling with, especially with phase-changing materials, where you have to properly set those on the numerical model, and also expect a correct outcome. So yes, pretty much the boundary conditions, the physics, and also the time that you need to process all the data, and also to know how to export those data from the numerical model, because it's not a straightforward procedure.
What about the mesh?
The mesh, actually, Paris helped me a lot, and we conducted preliminary investigations, and we compared them what the outcome was when the mesh was greater and when the mesh was coarser. And actually, the mesh plays a big role on the accuracy of the results, because our numerical models weren't that geometry complicated. We were able to escape with having the best, with choosing the best preset for the mesh. But as I know now through my experience, for a much complex geometry, that would be something that you have to investigate.
Luca, I don't have any other questions. Petro, I don't know if somebody else would like to ask something. Petro,
you are mute. You are mute.
Pare, I think go ahead and finish, so we don't have to come back and forth, and then we unless anybody else has a different idea.
I don't have anything else to ask.
Say it again.
I don't have anything else to ask, Petro. I'm done.
Okay. I thought you had another one. Okay. Adrius, you want to comment or
Yep.
ask?
Yes, thank you for the presentation. Paris already asked a couple of questions that I also wrote. The validation was reported in the work, and I was also having a question regarding the grid dependency. Maybe I will ask about the practical implications of the work. Loucas, in your work, you write that simulations basically can help to make buildings more efficient. How do you believe that this approach can help in the practical terms for engineers, and especially with the boundary conditions when engineers don't know exactly the boundary conditions, what to put in the simulations? So I just wonder, can you comment your own approach, how this work can contribute to practical engineering from your perspective?
Yes. So the way that I see this, I would approach this problem is find a manufacturer where he specifically designs and builds his own building materials, so he knows exactly all the properties of the material, and also he pretty much knows where the materials will be placed, so the ambient conditions will be well known, because that plays a big role on the accuracy of the numerical simulation. From the practical perspective, as the technology evolves, and we also now have the cloud computing processing power, these tools would be much more easier accessible to people without expensive setups and high performance computers. And this is something that a lot of big companies are promoting now. So for example, SolidWorks is now promoting the cloud service, where you don't even need a very powerful computer. You can just buy the software and then use their computational power of the cloud to solve complex geometries. So for my first comment, as I said earlier, boundary conditions play a big role. So this would be much more practical for someone who manufactures and knows exactly the materials and the ambient conditions. Otherwise, as we also see their technology evolving, now we have much cheaper weather stations, much cheaper thermocouples with data loggers, so they can easily do a preliminary testing, and as we did with the double skin facade, and construct something in a small scale, and validate the model, and with the same principle construct something much more bigger, but this time you can rely on it and change something, and you know that what you change will give me the right outcome. So maybe something, a new material that they get cheaper, and they want to see, and they want to see if it actually will be good for the right case.
Okay, so basically your suggestion is product design and product development, yes? All right. Otherwise, I don't have other questions. I also would like to congratulate you, and the amount of simulations and the work that you reported is really impressive, and you use different tools and different methods. So I'm sure you will do very well as a researcher. So that will be all from my side.
Andrew. Thank you very much, Andrew, and for your valuable feedback. And thank you for joining me today.
Giorgio, you know, connect.
Luca, congratulations for the work you have done. I like the fact that you're doing all these things with grid, with mesh and different resolutions. You know, I would like to have an explanation, because it's very interesting for me as well. I'm referring to the third case that you have studied. And if I understand well, you have one riser which consists from a group of interconnected risers. That's correct, yes?
Yes.
And those who are capable of heating the fluid more efficiently, achieving higher higher temperatures. Where on your second case that you analyze, I thought that you are looking at the impact on the thermal performance of the installation.
For the case study 3.
2. No, from 3 we understand that it's one riser and it consists of many risers. On the second case that you analyze.
On the second system, you mean?
On the the second study, which you reveal, you have the impact of material properties there, if I understand well. Thickness, placement of thermal performance.
Yes, we had multiple configurations. We had thicker insulation. In some cases, we had double the insulation. And that insulation was placed on the external, on the internal, and in total, we are 25 configurations.
All right. From all those configurations, you end up to something
Mr. Yorgos is for the built-in integrated case.
I'm asking you presented this a second study. You said the second scenario.
For the PCM.
Yeah, for the PCM.
Okay.
So,
Luca, you may wanna put your slide there just to.
Yes, of course. So this is a case study 2.
That's a case study 2. Well, here you said that you have the impact of material properties, the thermal performance, insulation placement. Having this case in mind now, and going to the scenario number 3, to the third one you have, that you are having, that's something different. Can these two be combined together?
This is a geometry built in the numerical model.
All right. The concept of these two things.
Yes.
The riser on the one hand, third case study you have shown to us, with the second case study.
This one.
No, this.
This is example. This is a case study where a multiple group of risers were interconnected. Here in this particular demonstration, we have 3 fluid inputs.
I understand that. So,
I am missing here because this was done with a cross section of the SolidWorks. Here is missing one interconnection.
All right. Well, what was my question? Let's say I wanted to see if the know-how from the third case can fit with the second, or the know-how from the second case can come and support your third case.
Okay.
So can you have a combination of these two?
You can have.
Geometry might be different, of course.
Okay, so the difference is here we have a closed system, and this is
Yorgo, we may want to simplify the question because
I can answer. This system is a closed loop system. This is where our tank is, and we have forced convection operating the numerical model. So this model is exposed to ambient temperature and ambient and the solar radiation.
Okay.
And the way we configure the boundary conditions, let me find the slide. So here you can see for this particular case, the solar radiation angle. This is how we change the solar radiation angles facing the numerical model. The red arrow indicates the ambient temperature. These two were profiles, and these two were derived from the extracted data from the QGIS tool. So now we have ambient conditions, and these were imposed in the model with the use of interpolation. So for each hour, we have different temperature, different solar radiation.
Okay, actually, Loucas, I understand the whole concept. I have seen that you have done tremendous work. You have done a lot of simulations and a lot of analysis. I was going to ask you also about the validation, but the previous two questions from Andrews and from Baris, they covered the issue. So I will not go to validation, which is ultra important to make sure that what you are simulating reflects the actual scenario in real life. So I think I don't have anything else to ask, just to congratulate you for all this good work.
Thank you very much, Mr.
Thank you. Michali,
Alexandros Karalambidis is here with us in the room. Professor Karalambidis from the back.
okay. Does he want to? I think Michalis can ask questions, Pari, and then he can also jump in if he wants to have a comment.
Luca Muhal, I would like to congratulate you about your work. It's a considerable piece of work. And I do have a couple of questions from my side of expertise. The whole aim of this PhD, as I understand it, is to assess various alternative either configurations of a building or alternative building materials in order to achieve energy efficiency. Energy efficiency meaning that you consume less energy. The economic analysis of this is very important to a potential user or a potential investor. And if I remember correctly, you showed the slide regarding the payback period of the alternative materials. Can you please show us this slide?
It wasn't, this was, let me see, let me find the results.
I think it's
So
maybe
like
slide
heat map.
23.
Heat map. Yes, that's it. So I would like to ask you, you see, you have energy payback periods ranging from 3 years to 30 years. So first of all, I would like to ask you, what price of energy did you take? The price of energy before the crisis, the Ukraine crisis, or the price of energy after the Ukraine crisis? Or you took an average price of energy over the past 10 years? Because it's very important to have, in some cases, the triple time the price of energy in the last year after the Ukraine crisis.
It was before the crisis.
So it might be worth noting that taking into consideration the current situation of the volatile energy market, this payback period might fall substantially.
Yes, this could be different. It could be a different outcome. Yes.
Yes. So this is something that you should note you should take a note in your PhD thesis that taking into consideration the current developments in energy prices, these payback periods might be considerably less.
Okay. Yes, but this was this is not have nothing to do with a numerical process. The outcome of the numerical model would be the same.
Yes, I agree with you, but it advocates, it is in favor of your argument that the energy efficiency is an indicative measure to take.
Yes, I totally agree. We have to always use.
And I have another question. The energy payback period. Did you use a discounted energy payback period or a simple energy payback period? Because as we learn in energy economics, €1 you spent today, it was considerably more than €1 you save 30 years from today. So the energy payback analysis is a discounted energy payback analysis or a simple energy payback analysis?
It was a simple energy payback. Yes.
Okay. That's it from myself. Thank you very much.
Okay, good. Pari, is Mr. Karalambidis there? Dr. Karalambidis is there. You want to ask or comment or something?
We just to some questions.
Thank you, Luca. Yeah, the work you did was a lot, and the quality you have the publications. So I'm not going to ask any of that. So it's basically points to make your thesis better. And some questions that might come out. You will see some comments. I'm not going to go through all of them because there's no need now. The one question I wanted to ask, the rest you can read it, I will leave it here. How would you compare your results from others that did similar studies? How similar are they? How different are they?
This is something that this is a process that I already did because I did a lot of literature reviews. So this is how I developed my methodology. I was doing a lot of comparison with what other did and what the results were the outcome of their studies. So also another form of validation.
Okay. And the rest, I'm not going to take up time. You will see it here. If you make the changes, it will improve the structure. Like at the beginning and the introduction, you can say about what I did and what's the structure of the thesis. Mm-hmm. At the end, you can have a table of the barriers, the main findings, just to make it easier for the viewer. I'll leave you the copy.
Okay.
Again,
thank you very much for the valuable feedback. I will for sure consider it.
Okay.
Yes, Luca, to tell you the truth, I had a few questions, but luckily I am going to talk last, so most of the people, most of the questions are answered already. One question that I wanted to ask is, what was the rationale for choosing this particular case studies? I mean, why did you choose those and not something else? That's a question. It's I'm sure
these were part of the projects that Sustainable Energy Research Group were involved. So
okay, so it was pretty much a given set, and you work on those. It's not because you went through the literature and you consider that these are the best possible options or something.
Given the nature of the projects, I had to develop those models, but the approach was entirely done by me. So I think
yes. I mean, I understand that. I was just wondering.
I think they are the best.
Okay.
So the answer to your question is that I think they are, for the current situation, they were the best option at the current situation.
Okay. And another question I have, Luca, and you may want to take a couple of minutes before you answer, is obviously you have done a lot of work, you published this work, and I'm sure you have done a lot more that is not shown here. I mean, this is normally the case. But normally for a PhD, Luca, you have to somehow contribute to the current state of the art. In other words, you have to present something that you have either developed or found out, etc. And I am sure you have said this in different places because you have done all this work and you have all these papers, etc. But I think it would probably be a good idea, I don't know if Paris agrees, to have somewhere in your thesis, possibly at somewhere in the early chapters somewhere, to actually state what do you think was your contribution to the current state of the art, so the reader of this work can identify right from the beginning, you know, you have done all this work and then eventually you came up to this interesting or valuable or result, which is your contribution to the state of the art. That's normally the major, let's say, requirement for a PhD. So that's a suggestion. You can discuss this with Paris and maybe add a paragraph stating that. And the other one, just not with regards to the presentation, we probably have discussed this with Paris, but what do you plan to do, Luca? Are you, I mean, after today, are you staying in research? Are you going somewhere to work? Are you going to be a researcher? Are you going to pursue an academic position? What are your plans?
I'm particularly interested in working in the design and in the design industry, and being involved with CAD software like SolidWorks and Console, the one that I used to develop those numerical models, because I think it's something that will eventually catch up. This will be eventually a standard procedure, I think.
So you consulting?
There are a lot of companies now that do design and analysis for things that they never did before. So,
okay,
I am interested in working on this sector. Yes.
Well, good luck. I'm sure you are going to do well. You have done a good job, and I also want to congratulate you. I don't know, Paris, what do you think? I don't know if anybody has a follow-up question, or if you want to add anything else now that everybody's commented or pretty much gave his input.
Petro, I think we can ask Loucas to leave the room and have a brief discussion about his work. Yes?
Yeah, if there is no other question, then yes.
Okay. Thank you again all for joining me today.
All right, Loucas.
So, okay, we have an open mic, so the student will be listening to us. But in any case, Petro, would you like to coordinate a bit the discussion? I think we should decide for his whether he can.
Yeah, Barry, are you taking some notes? Are you taking some minutes?
We are recording.
Yeah, so it's recorded. Unless you want to do that, I mean, because you have in front of you a set of things that have to be prepared. So if you have any questions,
I will do them. Let's have a brief discussion whether we agree on having him as a PhD student. Actually, if I'm allowed to make the recommendation, I would say that Loucas was a hardworking researcher the past 3 years. Andrews, Petros, you experienced his work based on the super project Petros, all the simulations were conducted by him. Andrews, I think you had the opportunity to see him working in the secondments of the EUMA project. He actually had a very good paper there as a first author in a very good journal, Measurements, and he didn't even mention any of his work there, which was more experimental work. Okay, in general, Loucas, he's very good in doing simulation, in working with numerical models. He can achieve a lot. He did a great work. Okay, I will be honest with you, I didn't have much time to spend with his dissertation, what he delivered, the text, but I think that overall I have a very positive, let's say, opinion for his work, and I would be positive of naming him as a PhD holder from our department. He will actually be the third or the fourth PhD, let's say, graduate from the mechanical engineering department of Frederick University, and I believe that he deserves that. So my position is positive for him, and I would also suggest to, we can also discuss on his grade. I would suggest a high grade for him as well, either 9 or 10, something like that. So Petro, this is my opinion for.
Okay, Andrew, what do you? Do we have to give grades, Barry? I think it's pass-fail, right?
It's pass-fail right now, yes.
Yes. So, okay, and because you mentioned the grade, Andrews, what is your take for this?
Yeah, I'm positive that he should be granted the PhD. No doubt about that. I also had the chance to work with Loucas. I really like the way he works, and I think he can really work both as a researcher and, of course, in industry with some development. So no problem. Yeah, no further comments.
Yes, I would like to support Loucas to become a PhD holder. I think he's done a good job a lot of simulations, and he proved that he did make a contribution. As Petros' question was that what is the contribution to knowledge? I think he did the contribution to knowledge.
No, the comment was that the contribution is there, but it's not stated somewhere, so it's shown there right from the start.
Right.
That was the comment, not
Okay.
whether there is any contribution.
Become allowed to comment. We have noticed that a few days ago, and that is why I asked him to add some slides at the beginning of his presentation about the novel developments of his work and how he contributed to science. And however, this was not in his dissertation, but he can certainly include some elements of that.
If you think, Barry, if you think it's because sometimes we take something to read, it's so many pages. At some point, you just skim through, and you may miss something important. Whereas if the important things are stated from the start or in the conclusions, normally it's easier to be found. That's why I mentioned that. Not okay, Michali, what do you think?
Well, from the court and from what the people had to say that work with Loucas, undoubtedly he has to be awarded a PhD. Yes, I do agree with awarding a PhD to Loucas, no doubt about that.
Good. Alexandros?
The same. All the comments I have are cosmetic, let's call it like that, to make the document that will stay better. So it's up to Baris to kind of look over it, make sure if he wants to, if he agrees with Baris, then you do them. If you don't like the structure, it's up to you, but it's just my ideas. The rest was just fine.
Okay. It's also positive. I also have a positive vote for this, Barry. So you can congratulate him that he did very
Shall
well.
we call him in the room and announce that to him? Or?
Do we have to discuss anything else? Do you want anything else to ask from us? Paperwork?
I don't know if anyone else. I can just call Loucas to join.
Okay.
Petros Loucas is here.
Loucas, first of all, I want to congratulate you for your work. I mean, we have mentioned that already, but now it's also official. Your committee thinks that you did a very good job, and of course, you are very much deserving this PhD. So congratulations.
Thank you very much, Petro. Thank you, everyone. Thank you very much.
It's very weird to class. Everyone's here.
In the virtual environment, thank you very much.
Okay.
Loucas, he holds a record because this is his 4th degree at Frederick. So he did his BSc here as automotive engineer. He did his master's in energy systems and the built environment. He did his master's in MBA. And he also received now his PhD. So he possesses 4 degrees from Frederick. I think
He is the oldest person.
And Paris, I think he can always start something parallel in civil. He can start with his BSc in civil now, and then
actually today he will start a new degree in computer engineering, software engineering.
Okay, computer engineering. That's fine. Okay.
Congratulations, Loucas.
Thank you very much, Andrews. Thank you.
Thank you very much, Loucas. Congratulations.
Thank you, Mr. Harris.
Bravo, Loucas. Well done.
Thank you.
There is a prerequisite, Loucas. Mr. Karagiorgis has some comments. Yes, you have to integrate them as well and deliver a hard copy for our library with indeed a hard copy.
I have the instructions.
Okay,
great. I will proceed as recommended.
Thanks. Petros, do we have something else?
Unless you want any information from us, Paris, before we go, if it's something you can communicate through email, I don't know.
Yes, I will circulate the minutes for your approval and your signature, and we can convey them to the department.
All right.
Perfect. Okay.
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 Thank you very much.
Well,
bye to all.
so, see you guys.
Bye.
Thank you again. Thank you very much.
Bye.
Andrews,
Thank you.
Andrews.
Yep.
So we are meeting on the 26th, I guess, right? 27.
Yes. Yeah.
So everything is said. It's just because I never talked to you, just communicate through email. So I look forward to that.
Yeah. Me too. Looking forward to greeting you in Kaunas.
Okay. All right.
Thank you.
See you, Paris. Bye.
Bye.
Bye, ciao.
Paris, έχεις με τίποτε?
Φίλε, να μιλήσουμε ένα στο τηλέφωνο. Εντάξει.
Εντάξει, οκ. Μια χαρά. Εντάξει, φίλε. Πάει, να είσαι καλά. Πάει.
Adesso stop share.
Stop share, c'è questo.
Ce l'ho in